Hey everybody, so today we're going to be doing a different type of video because I've got my mom here to record for me. Say hi to YouTube, Mom.
Hi everybody. Nice to see you.
So if you come with me, Mom, we're going to be doing what's called a Fourier transform. This specific Fourier transform popped up in my quantum mechanics textbook when it comes from switching Gaussian wave packet from the position space to the momentum space. And so what a Fourier transform does is it takes a function of one variable and it transforms it to a function of another. In this case, we're taking a function of x and we're going to transform it into a function of p. And so the way that this is going to work is we have this form for the Fourier transform. It's an integral transform where we have this thing here, which is called the kernel of the Fourier transform. And using that kernel, we're going to multiply it inside the integrand by the position space wave function, which is shown right here. Come a little closer on. There's our position space wave function. And so we're just going to plug that into our integrand here, and using a couple of nice tricks inside of our integral, we'll be able to go ahead and complete this problem. So the first thing that we're going to have to do is we're going to have to go ahead and rewrite our integrand with the position space wave function inside. And so instead of rewriting the whole thing, what I'm going to go ahead and do is I'm going to group these two constants together in the beginning and we'll deal with them at the end. So for now, I'm just going to say that this product of these two constants is just going to be called n. And so in that case, our momentum space wave function, p brackets I, is going to be equal to n times the integral from negative infinity to infinity of e to the negative I px over h bar multiplied by e to the negative x squared over 2a squared dx. And so the way that we're going to have to solve this integral is we're going to have to do some messing around with our exponential functions here. And so what I'm going to go ahead and do is I'm going to kind of forget the integral for a second and just play around with this exponential product. So if you're unfamiliar with exponential products, if you have the product of two exponential functions, say e to the x times e to the x, this is the same thing as e to the x plus x, or e to the 2x. So what we're going to do for this is we're going to do that same rule, which is going to be a little bit more involved. So what we're going to have here with this product is it's going to actually be negative I px over h bar minus x squared over 2a squared. And so now what I'm going to do here is I'm going to rearrange things a little bit and factor some things out. And then we're going to actually use the known formula for completing the square. And once I do that, it's going to put our function in the exponent in a real nice clean form to where we can actually solve our integral and complete our transform. So what I'm going to do is first I'm going to write x squared as the leading term since it's our highest power minus I px over h bar. And now what I'm going to do is I'm going to factor out that 1 over 2a squared. So when I do that with a negative as well, it's going to leave just x squared by itself as our leading term, and plus, because I factored that negative, 2a squared I px over h bar. Since I factored this term out and it wasn't present in the second term, I have to multiply it in to make sure everything is equivalent. And now that I have this, I'm going to go ahead and use my completing the square formula. So if you'll come in close to me here, Mom. For any quadratic function, ax squared plus bx plus c, you can rewrite it in this expanded form, which is known as completing the square. And so we have a quadratic function here, x squared plus 2a squared I px over h bar. And so now I just need to write out what's a and what's b and what's c, and I can rewrite it in this form. So for our case, the reason I did this factoring is so our a value is going to be 1, and our b value is going to be 2a squared I p over h bar, and c conveniently is going to be 0. So Now this form, since we know c is 0, is going to reduce to x plus b over 2a squared minus b squared over 4a squared. And remember, we said that a is equal to 1 and b is equal to 2a squared ip over h bar. So now we're going to rewrite our exponents in this general form. So what it's going to be is it's going to be x plus b, which is this whole thing here, divided by 2a, and since a is 1, it's just going to be over 2. And so those 2's are going to cancel, and so we're just going to be left with x plus a squared ip over h bar squared. Then it'll be minus b squared. So for us, b squared is going to be this whole thing squared. So 2a squared ip over h bar squared. And that whole thing is divided by 4a squared. And since a is 1, it's just going to be divided by 4. Okay? And so now I'll just clean up this term, and then we'll be ready to move forward. So just rewriting this first term here. And now up top, we're going to have 4a squared, I squared, p squared over h bar squared. And so that'll be this, or sorry, a to the 4th, I squared, p squared, h bar squared over 4. And so now again, just rewriting. So if you'll notice, this 4, this is a complex fraction. And so this is just a 4 over 1, so when we flip it back in, the 4's will cancel. And so I can go ahead and get rid of that. And then I squared is equal to -1, since the square root of -1 is equal to I. So that's just going to give our negative term to become a plus. And so now we're going to have so now what we're going to have is we're going to have a to the 4th p squared over h bar squared. The 4's cancel. And now what we can do is we can go ahead and factor here. Yes, that's correct. And so what you're going to notice is we can just plug this form back in to this. We've expanded this term here into this term, and now we're just going to factor that constant back in that we took out. And so we'll go ahead and take care of this one first, because if you'll notice, this term no longer has an x in it, and so we can treat it as a constant in our integrand, because our integrand is with respect to x, not p. And so if we multiply the -1 over 2a squared back in, a to the 4th will cancel with the a squared, and we're going to be left with a squared p squared over 2 h bar squared, and that whole thing is going to be negative. And that's raised to the e. And now we're going to take that outside of our integrand and go ahead and rewrite our integral with this term now being this term. So it's e to the x plus a squared ip over h bar squared. And now what we're going to do is we're going to shift our integral and our constant back in here. This is still multiplied by -1 over 2a squared. And so now what I'm going to do is I'm going to shift our variable. So we're going to let x become x minus a squared ip over h bar. And what that's going to do is that's going to make our integral become e to the x squared over 2a squared, and that's negative dx, and then we'll just bring this constant with us. And this is a known Gaussian integral, which I have written out here. I won't show you how to do it in this video, but I'd be happy to in another one. This just is going to reduce to a times square root of 2 pi. So if you remember, we still had that constant n out front, and now we've got e to the negative a squared p squared over 2h bar squared. And this integral has now reduced to a times the square root of 2 pi. And so now what I'm going to do is give myself some room, take care of these constants, and we will have completed our Fourier transform. And so let's move this. N, if you remember, was the product of 1 over the square root of a times the square root of pi times 1 over the square root of 2 pi h bar, and now times a square root of 2 pi. So what I'm going to do is I'm going to rewrite this second term so you can easily see where the cancellation is. This second term is the same thing as the square root of 2 pi times the square root of h bar. And this third term is still a square root of 2 pi. So you notice these will cancel. And we're going to be left with 1 over the square root of a times the square root of pi times a over the square root of h bar. Now, a over the square root of a is the same thing as a to the 1 over a to the 1/2. So that just becomes a to the 1/2 in the numerator, or the square root of a. So now this is going to reduce to the square root of a over the square root of h bar times the square root of pi, or more cleanly, the whole square root of a over h bar square root of pi. Now that we have our constant, we can multiply it back by our exponential function. And that completes our Fourier transform of the position space wave function into the momentum space wave function. We get another Gaussian wave packet in the momentum space. If you notice, there's no more x's, only p. And you can do this both ways. Be happy to do it both ways. That's something you guys want to see. But more quantum mechanics on the way, because I'm finally in the class, and definitely will be doing some matrix mechanics videos, hopefully in the next few months. Bye.
Bye.